Welcome, everyone. Today, we are exploring a foundational pillar of MLOps infrastructure, configuring GitHub integration with Azure Machine Learning to enable secure access. Let's dive into how we can automate our ML workloads safely and effectively. Let's begin with the core concept. Integrating GitHub with Azure Machine Learning is how we bring DevOps automation to data science. But there is a major challenge. GitHub is an external system. How does it securely tell Azure, I am authorized to train a model on your compute cluster? If we do this wrong, we expose our proprietary data and expensive compute resources to the public internet. If we do it right, we enable rapid, reliable deployment of ML artifacts. We achieve this by establishing a secure trust bridge using Azure Enter ID and GitHub secrets. We never hardcode passwords. This integration shifts our process from manual, risky deployments to a systematic, highly secure engineering discipline. Take a look at this high-level architecture. On the left, we have our GitHub Actions CI/CD pipeline, representing our automation. In the middle is the trust boundary. GitHub cannot simply bypass this. It must provide secure authentication. Once validated, the boundary opens, granting the pipeline authorized access to the Azure ML workspace on the right, allowing it to securely interact with our compute targets and data stores. To let GitHub talk to Azure, we need a digital identity. We do not use a human's email and password. Instead, we use a service principal. A service principal is essentially a user account designed exclusively for applications and automated tools. Why is this critical? Because relying on a developer's personal credentials creates a single point of failure. If they leave the company, the pipeline breaks. It's also a massive security risk. By creating a service principal, we can tightly control what GitHub is allowed to do. We use the Azure CLI to create this identity and assign it a specific role, like workspace contributor, scoped exactly to our ML workspace. It gets no access to anything else in our Azure tenant. This diagram shows the creation process. We use the Azure CLI to create the service principal. The most critical step is the assign role and scope decision block. We explicitly scope the permissions to a single ML workspace and grant it the contributor role. Notice that access to other corporate resources is entirely denied. Finally, the process generates a client ID and secret the digital keys we will need shortly. Now that we have our service principal's credentials, where do we put them? The golden rule of secure MLOps is never, ever commit secrets in plain text to your repository. If you hardcode a credential, it becomes visible to anyone with read access and can easily be scraped by malicious actors. Instead, we use GitHub secrets. These are encrypted environment variables stored securely within the GitHub platform. You simply navigate to your repository settings and paste the service principal's JSON output into a new secret, typically named Azure Credentials. When the pipeline runs, GitHub injects this secret into the runner's memory. As a deep dive security feature, GitHub actively scans the execution logs. If any process tries to print your secret, GitHub automatically redacts it from the output. Let's walk through the lifecycle of a secret in this sequence diagram. The ML engineer pastes the JSON credentials into the GitHub settings UI. GitHub instantly encrypts and stores it. When a workflow is triggered, the GitHub Actions runner securely requests the secret and injects it directly into memory. Crucially, look at the final step. If the runner attempts to output the credential to the action logs, the system intercepts and redacts it, keeping your data entirely safe. As your team scales, a single ML workspace is no longer sufficient. Enterprise MLOps requires strict separation between development, staging, and production. This means we need environment-level isolation. If a data scientist is experimenting with new code, we absolutely cannot allow that code to execute using production credentials. It could corrupt a live model. To solve this, we use GitHub environments. We create an environment called dev and store the dev workspace credentials there, and a separate environment called prod with production credentials. In your workflow, you specify which environment the job belongs to. As an added layer of security, we can mandate required reviewers on the prod environment. Even if the automated tests pass, the pipeline halts until a senior architect explicitly approves the run against the production cluster. Here we see environment routing in action. The pipeline checks the branch context. Feature branches route to the dev environment, pulling dev credentials and executing in the dev workspace. Main branch deployments route to the prod environment. But notice the halt the human review gate. The pipeline pauses, waiting for a human approver. Only upon approval does it fetch the production credentials and interact with the live production workspace. Storing secrets securely is great, but what if we could eliminate secrets entirely? Welcome to the modern standard, keyless authentication using OpenID Connect, or OIDC. Traditionally, we had to manage long-lived secrets, which carry the risk of theft and require tedious manual rotation policies. With federated identity credentials, we remove the secret. Instead, we configure Azure Enter ID to cryptographically trust your specific GitHub repository. When your pipeline runs, GitHub generates a short-lived identity token and hands it to Azure. Azure verifies the token, says, "I trust this repository," and grants temporary access to the ML workspace. It is vastly more secure because there are no passwords to steal, and the temporary access expires immediately after the pipeline finishes. This sequence diagram illustrates the beauty of keyless authentication. The GitHub action asks its internal OIDC provider for an identity token. It takes that token and presents it to Azure Enter ID via the Azure/login action. Azure checks its federated trust settings. Because they match, Azure issues a short-lived access token. The GitHub action then uses this temporary token to submit the machine learning job to Azure ML. We have our secure authentication configured in Azure and GitHub. Now, we must tie it all together using code. We do this by creating a YAML workflow file in our repository. This YAML file is the blueprint of our automation. We define triggers, for instance, running the workflow only when a pull request is merged. Inside the job, we define the environment to ensure GitHub applies the correct protection rules and fetches the correct credentials. The most critical step in the YAML is the Azure/login action. This action takes the secrets or the keyless OIDC configuration we set up and establishes the secure session. Only after this step succeeds does the pipeline proceed to use the Azure ML CLI to actually submit the training job or deploy the model. Let's follow the logic of our YAML file. A pull request merge triggers the workflow. The very first thing it does is set the context to the production environment. It then executes the Azure/login action. This is a strict gateway. If authentication fails, the pipeline halts immediately, preventing unauthorized access. If it succeeds, it installs the Azure ML CLI and securely executes the command to create the machine learning job. Automation is powerful, but it is dangerous if we automate the deployment of bad code. Therefore, we must implement branch protection rules. In a secure MLOps environment, absolutely no one is allowed to push code directly to the main branch. Not even the lead architect. If a data scientist wants to update a hyperparameter, they must create a feature branch and open a pull request. By requiring pull requests and mandatory peer approvals, we ensure every change is reviewed. Taking it a step further, we mandate status checks. This means GitHub will run a preliminary ML evaluation job in a safe sandbox. If the model's accuracy drops, the status check fails, and the pull request is physically blocked from merging into main, protecting our production environment. This diagram highlights our defensive perimeter. If a data scientist attempts a direct push to main, the branch protection immediately rejects it. They must follow the proper path, open a pull request. This triggers automated tests. If the tests fail, the merge is blocked. If they pass, it goes to a peer review. Only after human approval does the code merge to main, triggering our secure deployment. Let's apply this to a real-time, highly critical use case. Prosware is a healthcare startup building a diabetes classification model. They must frequently retrain this model as new patient data arrives. Because this is healthcare, security and HIPAA compliance are paramount. They cannot hand out Azure passwords to data scientists. By implementing our secure architecture, data scientists safely experiment in an isolated dev environment. When they open a pull request for the final model, they merge it into the main branch. This triggers a GitHub action that uses keyless federated authentication to securely access the prod Azure ML workspace. It deploys the model to a secure online endpoint seamlessly, with zero credentials stored in code, zero human touch on production servers, and complete auditability. In this final scenario flow, the dev team's model updates merge via a pull request. This engages the keyless OIDC authentication, exchanging an identity token with Azure Enter ID. Once securely authorized, the pipeline interacts exclusively with the Azure ML production workspace to deploy the updated diabetes model. The healthcare web app consumes this fresh, highly secure endpoint, delivering life-saving analytics without compromising compliance.